You're moving faster than a bullet. Earth carries you around the sun at over 60,000 miles an hour. Our solar system rides inside an invisible bubble. The sun blows around itself. Today, we cross that bubble and keep going. We ride past Pluto, past the icy junkyard of the Kuiper Belt, out to the wall where the solar wind finally dies. We push through a storm of cosmic radiation the sun can no longer block. Beyond that wall waits a frozen shell of comets so wide it takes half a year for light to cross it. Voyager 1 and Voyager 2, launched in 1977, already made this trip, and they are still out there, sending back whispers from beyond our star's reach. If leaving home sounds like your kind of trip, tap like and subscribe before we go. Hold on, we are leaving the solar system. Picture the solar system shrunk down until Earth sits exactly 1 inch from the sun. On that scale, Neptune, the last real planet, sits about 30 feet away. Most people stop their picture right there and call that the edge. The true edge sits almost 10 feet farther out than that, past a scale model of Neptune, guarded by a wall made of nothing you can touch. That wall carries a name most people have never heard. Scientists call it the heliopause. It sits about 11 billion miles from the sun, so far that sunlight itself needs almost 16 hours to cross the gap. Compare that to the light warming your face on a summer afternoon. That light left the sun 8 minutes earlier. The light marking the true edge of our solar system left over 100 times longer ago than that. This wall is not solid. No spacecraft could crash into it the way a car hits a fence. It is a boundary drawn by pressure, the exact spot where the wind blowing off our own star finally runs out of strength, and the emptiness between the stars pushes back just as hard. Everything inside that wall belongs to the sun's territory. Every planet, every moon, every frozen chunk of rock tumbling through the dark. Everything past it belongs to something far bigger than our star. Only 2 human-made machines have ever crossed it. Both were built in the 1970s, both run on computers weaker than a basic calculator, and both are still working today, whispering signals back across billions of miles. Getting there took decades. Their path carried them past every planet, through a belt of frozen leftovers from the solar system's birth, and into a violent zone where the sun's own wind gets crushed against the wind of the galaxy itself. You're about to follow that same path, not through a telescope, not through a chart in a textbook, but stop by stop the way it actually happened, starting with the world every person on Earth already knows by name. Nobody has ever seen this wall through a telescope, because it gives off no light of its own. Scientists first predicted it decades before any spacecraft came close enough to check, using nothing but math and a basic understanding of how a star's wind should behave once it runs out of room to expand. A separate spacecraft, orbiting much closer to Earth, later mapped the wall's rough shape from a distance by catching faint particles bouncing backward off it, the same way a person standing in a dark room might map the walls by throwing a ball and listening for the sound of it bouncing back. Scientists still argue about the wall's exact position on any given day because it is not fixed. It breathes in and out with the sun's own moods, swelling when solar activity runs high and shrinking when the sun calms down, the way a lung expands and contracts only over years instead of seconds. Somewhere past that breathing wall, the wind from our star has already died out completely, replaced by particles that have drifted through the galaxy since long before Earth ever existed, some born in the explosion of a star that died millions of years ago. Nothing out there has ever felt the sun's warmth. Before reaching that cold, unfamiliar territory, there is one more stop everyone recognizes, a small, icy world sitting right at the doorway of true deep space. It once held the title of 9th planet. It lost that title, and it is about to prove why the argument over its name was never really the interesting part. The last familiar landmark before the true wilderness begins is Pluto. A scientist working alone in a small observatory found it in 1930, after months of comparing photographs of the night sky for anything that moved. For over 70 years, it wore the title of ninth planet, until a wave of new discoveries in the same region forced astronomers to draw a stricter line around what counts as a planet, and Pluto lost the title in 2006. The demotion never made Pluto boring. It sits almost 4 billion miles from the Sun on average, so far out that a single trip around its orbit takes about 248 years. Anyone born the year Pluto finishes one loop would already be long gone before it finished a second. The surface sits at roughly 375 degrees below 0 Fahrenheit, cold enough that nitrogen, a gas that fills the air you're breathing right now, freezes solid onto the ground like snow, then slowly turns back into gas as Pluto's slow orbit carries it slightly closer to the Sun. Pluto is not travelling alone. Its largest moon, Charon, is almost half its size, big enough that the two worlds do not orbit each other the normal way. Instead, they spin around a shared point of balance hanging in empty space between them, like two dancers holding hands and spinning around the spot exactly between their palms, neither one truly circling the other. Charon is not Pluto's only companion. 4 smaller moons circle the pair as well, tumbling through space at odd, unpredictable angles rather than spinning smoothly the way most moons do, likely because Charon's gravity is strong enough to knock their rotation off balance. Scientists believe all 5 moons formed from the same violent collision billions of years ago, when a smaller, icy body slammed into Pluto and scattered debris that later clumped back together in orbit, similar to the leading theory for how Earth's own moon formed. A spacecraft called New Horizons reached Pluto in 2015 after a 9-year journey, and it changed everything scientists thought they understood about small frozen worlds. Instead of a dead, cratered ball, cameras found towering mountains of water ice, a heart-shaped plain of frozen nitrogen so smooth it may still be shifting today, and hints buried in the data that an ocean of liquid water could be hiding far beneath the frozen crust. Standing on that surface, a person would not see the Sun as a bright disk the way it looks from Earth. It would look like an extremely bright star, casting light no stronger than a deep Earth twilight, even at high noon. Pluto sits inside a much larger neighbourhood, one most people never learn about in school. Hundreds of thousands of icy bodies orbit out here, leftover material from the exact moment the solar system formed, never pulled together into a real planet, never destroyed, just drifting in the dark for over 4 billion years. Pluto happens to be the most famous resident of that neighbourhood. It is nowhere close to the only one, and some of its neighbours hide details even stranger than a heart-shaped glacier or a moon that refuses to simply orbit in a normal circle. Past Pluto, the wilderness that scientists call the Kuiper Belt truly begins. Picture a belt of leftover construction materials circling the Sun, stretching from about 2.5 billion miles out to nearly 5 billion miles, packed with hundreds of thousands of icy bodies too small, too scattered, or too far apart to ever pull together into a true planet. Every object out here formed at the exact same time as Earth, the Sun, and every other planet, over 4 billion years ago. While the inner planets melted, cooled, and reshaped themselves again and again, these frozen bodies never got the chance. They are leftover ingredients from a meal that never finished cooking, frozen exactly the way they were the day the solar system took shape, which makes them some of the best time capsules available anywhere in space. Most Kuiper Belt objects are made of a mix of rock and ice, coated in dark reddish material formed when sunlight, faint as it is out here, slowly breaks apart simple frozen chemicals over billions of years. A handful of these objects grew large enough to pull themselves into a round shape under their own gravity, earning the title of dwarf planet, the same category Pluto now belongs to. The scale of this belt is difficult to picture using anything from daily life. It would take a commercial jet flying non-stop without ever landing more than 500 years just to cross it. Yet despite holding hundreds of thousands of icy worlds, the Kuiper Belt is so enormous and its residents so spread apart that a spacecraft could cruise straight through the middle of it and never come close enough to see one with the naked eye. Some of these objects follow calm, nearly circular paths around the Sun, quietly orbiting the same way for billions of years. Others follow orbits tilted at strange angles, evidence of ancient shoves from the gravity of Neptune, the giant planet that sits at the belt's inner edge. Neptune has spent the entire history of the solar system slowly rearranging this region, flinging some objects into new orbits, locking others into a steady rhythm that matches its own. 3 trips around the Sun for every 2 that Neptune makes. Comets that streak across Earth's night sky, the short-period kind that return every few years, are believed to be escapees from this very belt, nudged loose by a gravitational tug and sent falling toward the inner solar system, where sunlight finally warms them enough to grow a glowing tail. Every one of those comets carries a tiny piece of this frozen frontier into view from your own backyard. Deeper inside this belt hide world strange enough to have forced scientists to rewrite the rules for what counts as a planet in the first place, including one shaped less like a ball and more like a spinning football, and another that ended Pluto's solo reign as the only dwarf planet anyone had ever heard of. Buried inside the Kuiper Belt are worlds strange enough to have rewritten the rulebook. The discovery of one of them in 2005 caused the entire argument over Pluto's planetary status in the first place. That world is called Eris, and for years astronomers believed it might actually be more massive than Pluto, prompting an uncomfortable question. If Eris counted as a planet, shouldn't every other large icy body out here count too? Rather than expand the list of planets indefinitely, astronomers drew a firmer line, and both Pluto and Eris ended up on the dwarf planet side of it. Eris orbits even farther from the Sun than Pluto on average, and its surface runs so cold that its thin atmosphere is believed to freeze completely solid during the coldest stretch of its long orbit, coating the entire world in a thin layer of frost. Even stranger is Haumea, a dwarf planet spinning so fast that gravity has never managed to pull it into a proper sphere. Instead, it stretches into an elongated shape, closer to a football than a ball, because a single day on Haumea lasts under 4 hours, faster than any other large object known in the solar system. Spin a water balloon fast enough in your hands and it stretches the same way, bulging outward at the middle as it whips around. Haumea even carries its own thin ring, a feature scientists once assumed only large planets like Saturn could support. Then there is Makemake, a reddish world coated in frozen methane, discovered shortly after Eris and named after a creation deity from Easter Island tradition, keeping with the pattern of naming these distant worlds after gods tied to the cold and the unknown. Makemake orbits alone as far as anyone has found, with no confirmed large moon keeping it company the way Charon accompanies Pluto or a small moon orbits Haumea. Makemake held one more surprise. For years, astronomers assumed a world this small and this cold could not hold on to any atmosphere at all, since gravity that weak usually lets gas drift away into space within a short time. Then astronomers watched Makemake pass in front of a distant star and measured the starlight dimming in a pattern that revealed a thin, temporary haze clinging to the surface, evidence that a faint atmosphere can form and collapse again as the dwarf planet's extremely slow orbit carries it closer to, then farther from, the Sun's weak warmth. These 4 dwarf planets, Pluto, Eris, Haumea, and Makemake, represent only the largest, brightest, and easiest to spot residents of this region. Thousands of smaller bodies drift among them, some barely a few miles across, too small and dim for any telescope on Earth to have found yet. Every year brings the discovery of a few more, hinting that the true population of this belt may be far larger than current counts suggest. Standing on any of these worlds, a traveller would face nearly total darkness, relieved only by a distant star-sized sun and a sky glittering with stars far brighter and more numerous than anything visible from a city or even from the darkest countryside on Earth. The Kuiper Belt is not the only reservoir of comets in the solar system, but it is the source of the short-period kind, comets that swing past Earth on a predictable schedule, some returning every few years like clockwork. A separate, far larger reservoir of comets waits even farther out, one so distant it makes even this belt look like a nearby suburb, holding the long-period comets that streak into view only once every few centuries, if ever, having spent thousands of years drifting through the darkest, coldest part of the solar system before finally falling sunward. Every signal sent home from out here already takes hours to arrive. The next stop stretches that wait time even further, into a delay so long it starts to reshape how humans think about distance itself. Every signal your phone sends and receives feels instant, because the distances involved are so small that light barely notices the trip. Out past Pluto, the numbers stop feeling small. Light travels at about 186,000 miles every single second, fast enough to circle the entire planet Earth about 7 times before you could blink. Even at that staggering speed, light takes about 8 minutes to travel from the Sun to Earth. Reach Pluto, and that same beam of light needs more than 5 hours to arrive. Push out to the far edge of the Kuiper Belt, and the wait climbs past 7 hours. That delay is not just a fun fact. It became a real engineering headache the moment humans tried to fly a working spacecraft out here. When New Horizons flew past Pluto in 2015, any single command sent from Earth took over 4 hours just to reach the spacecraft, then another 4 hours for confirmation to travel back. A simple back-and-forth conversation, the kind that takes seconds between 2 people in the same room, took nearly 9 hours to complete across that gap. Engineers on the ground could not steer the spacecraft in real time the way a person drives a car. Every move had to be planned, written into code, and sent hours in advance, trusting the spacecraft to carry out its instructions correctly, with nobody available to fix a mistake in the moment. This delay also explains why sunlight out here feels so weak. Light does not just take longer to arrive, it also spreads out across a much larger area the farther it travels, growing dimmer with every mile the way a flashlight beam fades across a dark field. By the time sunlight reaches Pluto, it carries less than 1/1000th of the strength it has on Earth. Stand on the surface at high noon out there, and the brightest object in the sky would look barely different from a very intense star, nothing like the warm, glowing disk that lights up a summer afternoon back home. The very idea that light takes any time at all to travel anywhere was not obvious until scientists studied a different set of distant objects entirely. Centuries ago, an astronomer noticed that a moon circling Jupiter seemed to fall behind schedule whenever Earth swung to the far side of the Sun, and got ahead of schedule whenever Earth swung closer. The pattern only made sense if light itself needed real time to cross real distance, and that single observation gave humanity its first working estimate of the speed of light, long before anyone could measure it directly on Earth. Keep pushing outward, past the edge of the Kuiper Belt, and these numbers only grow more extreme. A message sent from the true edge of the solar system, the wall reached only twice in human history, takes nearly a full day to arrive back on Earth. Anyone controlling a spacecraft out there is not having a conversation. They are leaving a message, then waiting through an entire day of silence before any reply could possibly return. One spacecraft pushed straight through this widening delay and kept going anyway, chasing a target so small and so far away that finding it required some of the most precise navigation ever attempted, aimed at a frozen world scientists had not even discovered when the spacecraft first launched. That spacecraft is New Horizons, and its story did not end at Pluto. It began there. Launched in January of 2006, New Horizons left Earth faster than any spacecraft before it, crossing the orbit of the Moon in under 9 hours, a trip that took the Apollo astronauts 3 full days. Even at that blistering speed, the journey to Pluto still took 9.5 years, a reminder of just how enormous the distance really is. Along the way, the spacecraft swung past Jupiter, using the giant planet's gravity like a slingshot to pick up extra speed for the long stretch still ahead. After its historic flyby of Pluto in July of 2015, mission scientists faced a choice. The spacecraft still had fuel, power, and working instruments, but nothing obvious left to explore. Using the massive Hubble Space Telescope, They searched the region ahead of New Horizons for any object close enough to its path to visit, and found a small, dim world roughly 22 miles long, later named Arakoth, a word meaning sky in a Native American Powhatan language. On the very first moments of 2019, New Horizons flew past Arakoth from a distance of about 4 billion miles from the Sun, making it the most distant object any spacecraft has ever explored up close. What the cameras revealed stunned scientists watching from Earth. Arakoth turned out to be two separate icy lobes gently fused together, shaped almost like a lumpy snowman tumbling through the dark, formed when two smaller bodies drifted together so slowly, so gently, that they stuck rather than shattered on impact. Before settling on its final name, the object carried a temporary nickname chosen by the mission team, later replaced after public feedback and formal review by the body in charge of naming objects across the solar system. The switch mattered to the scientists involved, who wanted a name that honoured the region of space the object called home, rather than one borrowed from an unrelated part of history. Arakoth had likely never been disturbed since the solar system's birth, drifting undisturbed in the same cold, quiet orbit for over 4 billion years. Studying its surface gave scientists a direct look at building material from the earliest days of the solar system, material far more pristine than anything ever recovered from a planet, an asteroid, or even most comets, which get reshaped every time they swing close to the Sun's heat. New Horizons is still out there today, healthy, still transmitting, still drifting deeper into the Kuiper Belt with enough power expected to last into the 2030s. It carries a small canister holding a portion of the ashes of the astronomer who first discovered Pluto back in 1930, sending him on a final journey past the very world he found and out into the frozen belt beyond it. Not every object out here follows a calm, predictable path like Arakoth's. Some were flung by Neptune's gravity onto orbits so wild and so stretched that they carry these worlds farther from the Sun than almost anything else known, out to distances that make even the Kuiper Belt look small by comparison. Farther out than the main body of the Kuiper Belt lies a region scientists call the Scattered Disk, home to worlds thrown onto some of the strangest orbits in the entire solar system. Every object out here shares the same origin story. Long ago, each one drifted close enough to Neptune for the giant planet's gravity to grab hold and fling it outward, the same way a slingshot launches a stone much farther than a throwing arm ever could alone. Instead of settling into the Kuiper Belt's calmer, more circular paths, these worlds ended up on long, stretched, tilted loops that carry them wildly different distances from the Sun depending on where they sit in their orbit. The most famous resident of this scattered region is a small, deeply red world named Sedna. At its closest approach, Sedna still sits farther from the Sun than Pluto ever gets. At its farthest point, its orbit stretches out to roughly 87 billion miles, a distance so extreme that a single loop around the Sun takes over 11,000 years to complete. Sedna was discovered in 2003, and since that discovery, it has barely moved along its own orbit, because a journey that long makes even decades of observation look like a single frozen snapshot. Sedna's deep red colour sets it apart from almost every other object found this far from the Sun, second in redness only to the planet Mars itself. Scientists still debate what could have flung an object onto an orbit this extreme. Neptune's gravity alone cannot fully explain a stretch this dramatic, since Sedna never travels close enough to Neptune for a direct gravitational shove. Some scientists suspect a passing star billions of years ago tugged Sedna outward. Others wonder if an undiscovered planet, far larger than Earth, still hides somewhere in the darkness, quietly shaping the orbits of Sedna and a handful of similar worlds through gravity alone. Sedna is not alone in this puzzle. A handful of other extreme objects discovered in the years since share strangely similar tightly clustered orbits, as if something with real gravitational muscle keeps nudging them all into the same general alignment. That pattern is exactly what first pushed some astronomers to propose the existence of a large undiscovered planet lurking far beyond Neptune, one that has never been photographed directly, only suspected through the fingerprints it may be leaving on the orbits of its smaller, scattered neighbours. Whatever the true cause, Sedna and its scattered neighbours mark a turning point in this journey. These are the last individual worlds you will meet with a name, a discovery date, and a known orbit. Beyond this point, no single object stands out anymore. Instead, everything that matters becomes invisible, an ocean of charged particles streaming outward from the sun itself, filling every remaining mile of space between here and the true edge of the solar system, a bubble far larger than every planet, moon, and scattered world combined. That invisible ocean has a name, a shape, and a boundary all its own, and understanding it means leaving behind every rock, every moon, and every icy world explored so far to study something made entirely of wind. Every single object explored so far, from Pluto to Arrokoth to Sedna's wildly stretched orbit, sits inside something invisible and far larger than any of them. A bubble made entirely of wind, blown outward by the sun itself. That bubble is called the heliosphere, and it exists because the sun does not simply sit still and shine. It constantly sheds a stream of charged particles into space, called the solar wind, rushing outward in every direction at roughly 1 million miles per hour. That wind never stops. It has been blowing steadily for over 4.5 billion years, ever since the sun first ignited, and it will keep blowing for billions of years still to come. As this wind rushes outward, it pushes back against the thin haze of particles and magnetic fields drifting between the stars, called the interstellar medium. Picture a garden hose running constantly inside a swimming pool. The water from the hose pushes outward and carves out a bubble inside the pool water, before finally slowing down and blending into it. The sun's wind does something similar on a scale so massive it swallows every planet, every moon, and every icy world in the Kuiper Belt and scattered disk, all of it wrapped inside one enormous invisible bubble. The heliosphere is not a perfect sphere, because the sun itself is moving, dragging the entire solar system along with it in a long orbit around the centre of the galaxy. The interstellar wind blowing against that motion compresses the front of the bubble, while stretching the back into a long trailing tail, not unlike the shape of a comet or the wake trailing behind a boat cutting through water. Scientists are still refining exactly how long that tail stretches, since no spacecraft has ever travelled far enough in that direction to measure it directly. This solar wind itself was not always accepted science. In the 1950s, a young physicist proposed that the sun must constantly release a steady stream of particles into space, based purely on calculations, at a time when most of his colleagues assumed the space between planets was essentially empty and still. His idea was mocked in print by other scientists before spacecraft finally confirmed, just a few years later, that the wind was real, measurable, and blowing exactly as predicted, in every direction, every single second. Every planet in the solar system, along with every icy world discussed so far, orbits well inside this bubble, bathed constantly in the sun's wind and shielded by the enormous magnetic field the wind carries with it. That shield matters far more than most people realise. It blocks a large share of the dangerous high-energy radiation that constantly streams in from exploded stars scattered across the galaxy, radiation that would otherwise reach Earth's orbit at full strength. Travel far enough outward inside this bubble, and the sun's wind eventually runs out of room to keep expanding at full speed. It begins to slow, suddenly and dramatically, at a boundary that took 2 working spacecraft and several decades of patient travel to actually reach and measure directly. The sun's wind does not slow down gradually. It slams into an invisible wall of resistance and drops speed almost instantly at a boundary scientists call the termination shock. Near the sun, the solar wind screams outward at roughly 1 million miles per hour. Moving faster than sound can travel through the thin gas that makes up that wind, the same way a jet moving faster than sound creates a sonic boom in Earth's atmosphere. As that wind spreads across billions of miles, pushing against the resistance of the interstellar medium waiting beyond the bubble, it eventually can no longer maintain that supersonic speed. At the termination shock, the wind abruptly drops from a screaming rush down to a much slower, turbulent crawl, all within a boundary far thinner than the vast distances surrounding it. Voyager 1 became the first human-made object to cross this boundary, reaching it in December of 2004 at a distance of about 8.5 billion miles from the Sun. Its instruments recorded the solar wind speed plunging suddenly, along with a sharp jump in magnetic turbulence. Clear signs that the smooth, steady rush of wind experienced across most of the solar system had finally broken down. Voyager 2 crossed its own termination shock nearly 3 years later, in August of 2007, at a distance of about 7.5 billion miles, closer to the Sun than where its twin had crossed, since the two spacecraft travelled in different directions through a bubble that is not perfectly round. A jet breaking the sound barrier offers a useful comparison. As long as the jet flies faster than sound itself, the pressure waves it creates cannot spread out ahead of it, so they pile up into a single sharp shock wave, the boom people on the ground hear rolling past. Slow that same jet down below the speed of sound, and the shock wave disappears completely, replaced by smooth, ordinary airflow. The termination shock works on the same basic principle, just with a stream of charged particles instead of air, and a boundary billions of miles wide instead of a few feet. Two older spacecraft, Pioneer 10 and Pioneer 11, launched years before either Voyager and aimed in different directions entirely, never lived long enough to reach this boundary themselves. Both fell silent decades earlier, their power sources too weak to keep transmitting across such enormous distances, leaving the two Voyager spacecraft to complete a discovery that 4 separate missions had originally set out chasing. That difference in crossing distance told scientists something important. The heliosphere is lopsided, pushed and squeezed unevenly by the pressure of the interstellar wind blowing against it from a particular direction. The same way wind pressing against one side of a hot air balloon squeezes it into a slightly different shape than a perfectly round ball. Crossing the termination shock did not mean either spacecraft had left the solar system. Plenty of solar wind still surrounded them on the far side of that boundary, just moving slower and behaving far more chaotically than before. Both spacecraft still had years of travel remaining before reaching anything resembling the true edge, pushing through a churning, turbulent region that scientists had barely been able to predict before actually flying a spacecraft straight through it. That churning region waiting just past the termination shock turned out to be stranger, stormier, and far more difficult to cross than anyone on the ground had expected. Just past the termination shock lies a region unlike anything found closer to the Sun, a churning, turbulent zone scientists call the heliosheath. Picture a fast-moving river finally reaching the ocean. Right at the river's mouth, the calm, steady current does not simply vanish. It churns, swirls, and fights against the ocean's much larger body of water before finally blending in completely. The heliosheath behaves the same way. Solar wind that once rushed outward in a smooth, steady stream suddenly finds itself compressed, twisted, and slowed as it collides with the resistance of interstellar space, creating a wide, stormy buffer zone stretching for billions of miles. Inside this zone, the Sun's magnetic field, normally stretched into smooth, predictable spirals closer to home, gets crumpled and folded back on itself, creating tangled loops and unpredictable pockets of turbulence. Both Voyager spacecraft recorded violent, unexpected swings in magnetic field strength while crossing this region, along with strange bursts of radio noise that scientists still work to fully explain. Nothing about this zone behaves as smoothly or as predictably as the solar wind closer to the planets. Crossing the heliosheath took an enormous amount of time. Voyager 1 needed about 8 years to cross from the termination shock to the solar system's true outer edge, and Voyager 2 took a similar stretch of time along its own path. For years, mission scientists back on Earth had almost nothing new to report. watching instrument readings creep along slowly as both spacecraft push deeper into this stormy buffer, with no clear signal yet marking the true finish line. Data sent back from this region revealed something scientists had never predicted at all. Rather than one smooth, continuous magnetic field stretching across the entire heliosheath, instruments detected the field breaking apart into a foam of countless smaller magnetic bubbles, some stretching for millions of miles, others far smaller, packed together like bubbles crowding the surface of a pot of boiling water. Researchers still debate exactly how this magnetic foam forms and how long any single bubble survives before merging with its neighbours or breaking apart entirely. Radiation levels inside the heliosheath also began climbing well above anything recorded closer to the planets, a warning sign of the far harsher environment still waiting beyond it. Despite the turbulence, this region still technically belongs to the Sun. The heliosheath is filled with material that originally blew outward from our own star, however battered and rearranged it has become by the time it arrives out here. Anything sitting inside this zone still counts as living inside the solar system's bubble, protected, at least partially, by the last remaining traces of the Sun's magnetic shield. That protection does not last forever. Somewhere past this churning, storm-filled buffer, the last traces of solar wind finally run out completely, replaced by something that has never once come from the Sun, arriving instead from other stars scattered across the galaxy. Reaching that final boundary took Voyager 1 nearly 3.5 decades of continuous travel, and when its instruments finally detected the change, the signal was unmistakable. Voyager 1 launched from Earth on September 5, 1977, on a mission originally designed to study Jupiter and Saturn up close, nothing more ambitious than that. It flew past Jupiter in 1979, capturing the first detailed images of the giant planet's storms and its 4 largest moons, then reached Saturn the following year, revealing intricate detail in the planet's rings that no telescope on Earth had ever managed to resolve. After completing that original mission, engineers realized the spacecraft still had enough power, fuel, and working instruments to keep going, so they let it. Voyager 1 kept flying outward for decades, well past its planned lifetime, well past the point most people assumed it would stop transmitting, steadily approaching the outer edge of the solar system 1 mile at a time. By December of 2004, 27 years after launch, Voyager 1 became the first spacecraft in history to reach and cross the termination shock, the boundary where the Sun's supersonic wind abruptly slows down. Onboard instruments recorded the exact moment clearly, showing solar wind speed collapsing suddenly, along with a spike in magnetic turbulence that confirmed the spacecraft had truly crossed into a new region, rather than simply detecting a temporary fluctuation. At the time of that crossing, Voyager 1 was travelling at roughly 38,000 miles per hour relative to the Sun, fast enough to cross the entire continental United States in under 5 minutes, yet slow enough that reaching the termination shock still took nearly 3 decades of continuous travel. Every instrument still functioning on board had been built using technology from the 1970s, running on a computer far less powerful than a basic pocket calculator, and every single one still worked well enough to detect and confirm one of the most significant milestones in the history of space exploration. Bolted to the side of Voyager, 1 is a golden record, a physical disc carrying sounds and images meant to describe Earth to whoever might one day find it. Greetings recorded in dozens of languages, music selected from cultures across the planet, and simple diagrams explaining exactly how to play the recording back. A team of scientists assembled the record in a matter of weeks before launch, fully aware that the odds of it ever being discovered by another living being were incredibly small, yet building it anyway, treating the attempt itself as worth making. Crossing the termination shock made headlines around the world, yet scientists were careful to explain that this crossing did not mean Voyager 1 had left the solar system. Plenty of solar wind still surrounded the spacecraft on the far side of that boundary, simply moving slower and behaving far more chaotically than before. The true edge, the wall separating the Sun's territory from true interstellar space still sat years of travel farther out. Voyager 1 pressed onward into the turbulent heliosheath that lay ahead, its instruments recording readings unlike anything encountered during the previous 27 years of flight, inching closer to a boundary that no human-made object had ever reached before, one that would take almost another full decade to finally cross. Near the Sun, the solar wind rushes outward at close to 1 million miles per hour, fast enough to cross the entire distance from Earth to the Moon in about 15 minutes. That speed does not last. As the wind spreads outward across billions of miles, the same total energy gets stretched across an ever larger area. The same way a shout that feels loud right next to your ear fades into near silence across a football field. By the time the wind approaches the true outer edge of the solar system, its speed has dropped to roughly 250,000 miles per hour, still faster than almost anything humans have ever built, yet only a quarter of the raw speed it carried near its source. This gradual slowdown does more than just change a number on an instrument panel. It signals a fundamental shift in the balance of power taking place across this region. Closer to the Sun, the wind carries more than enough pressure to shove aside anything in its path, sweeping dust, radiation, and stray particles outward with ease. Farther out, that pressure keeps dropping, while the resistance from the interstellar medium, the thin haze of particles and magnetic fields filling the space between stars, remains essentially constant no matter how far the wind has travelled to get there. Eventually, those two forces reach a state of balance. The weakening push of the dying solar wind matches exactly against the steady resistance of interstellar space, and right at that precise point, the wind effectively stalls out completely, unable to push forward even one more mile. That exact location marks the true edge of the solar system, the boundary separating the Sun's territory from the vast emptiness beyond it. Working out exactly where that balance point sits took decades of careful measurement, since neither force involved can be weighed on a scale the way ordinary pressure can. Scientists had to track the solar wind's slowing speed at every distance a spacecraft managed to reach, then compare it against estimates of how much resistance the interstellar medium could realistically provide, refining the prediction again and again as new data arrived from farther and farther out. Picture a fast-moving river slowing as it widens into a broad delta before finally meeting the ocean. Near the river's source, the current runs fast and forceful. By the time it reaches the delta, spread thin across a much wider channel, that same current barely seems to move at all, right before blending completely into the still, endless water of the sea. The solar wind follows a strikingly similar pattern, just stretched across a distance of billions of miles instead of a few dozen. The exact spot where this dying wind finally gives out completely carries its own name, its own history, and its own dramatic first crossing, a boundary reached by human technology for the very first time in August of 2012, closing out a chapter of solar system exploration that had taken 35 years to complete. The exact spot where the Sun's dying wind finally gives out completely is called the heliopause, and it marks the true, undisputed edge of the solar system. Unlike the termination shock, which simply slows the solar wind down, the heliopause represents a complete handoff of territory. On one side sits the last remaining trace of material that originally blew outward from the Sun. On the other side sits material that has never once touched our star, drifting instead through the galaxy for millions or even billions of years, born in environments the Sun's wind has never come close to reaching. Crossing this boundary means leaving the Sun's neighbourhood entirely and entering someone else's. Voyager 1 reached this boundary on August 25, 2012, at a distance of about 11 billion miles from the Sun, becoming the first human-made object in history to leave the solar system completely. The crossing did not happen gradually. Instruments recorded the count of particles that had originated from the Sun collapsing to almost nothing within the span of just a few days, while at the exact same time, the count of high-energy particles arriving from elsewhere in the galaxy spiked dramatically, roughly doubling within that same short window. It was the clearest, sharpest signal the mission had ever recorded, an unmistakable line drawn between two completely different environments. Voyager 2 followed a different path through the solar system and reached its own crossing point on November 5, 2018, at a distance of just over 11 billion miles from the Sun as well, confirming that this boundary exists in more than one direction and behaves in a strikingly similar way no matter where a spacecraft happens to cross it. A separate spacecraft orbiting much closer to Earth and never travelling anywhere near this boundary itself has spent years mapping the heliopause from a distance, catching faint neutral particles that bounce backward off the wall and streak all the way back toward the inner solar system. Piecing together thousands of these faint returning particles lets scientists build a rough picture of the wall's uneven, lumpy shape without ever needing to send another spacecraft anywhere close to it directly. The heliopause is not a fixed line drawn permanently in space. It shifts and ripples constantly, swelling outward when the Sun becomes more active and shrinking back inward during quieter stretches of the Sun's roughly 11-year activity cycle, the same way a lung slowly expands and contracts, only stretched across years instead of seconds. That means the exact distance to the true edge of the solar system is different today than it was when either Voyager spacecraft made its historic crossing, and it will keep shifting for as long as the Sun continues to shine. Crossing this wall changes everything about the environment surrounding a spacecraft almost instantly, stripping away the last remaining protection the Sun's magnetic field once provided and exposing anything on the far side directly to a much harsher, more dangerous stretch of the galaxy, one that neither Voyager spacecraft had ever experienced in over 3 decades of flight. On August 25, 2012, Voyager 1 became the first object ever built by human hands to leave the solar system completely, and it happened at a distance so vast that the news did not even reach scientists back on Earth until more than a year later. The delay was not a failure of communication. It came from the sheer difficulty of confirming exactly what the data actually meant. When the count of solar particles collapsed, and the count of high-energy particles from beyond the solar system spiked, instruments recorded a dramatic change immediately, but one key detail did not match what scientists had originally predicted. Many expected the direction of the surrounding magnetic field to shift noticeably the moment Voyager 1 crossed into true interstellar space. Instead, the magnetic field direction barely changed at all, leaving room for genuine scientific disagreement over what the spacecraft had actually detected. It took careful analysis of a rare event, a burst of activity from the Sun itself that rippled outward and reached Voyager 1 many months after the original crossing, to finally settle the debate. That solar disturbance caused the plasma surrounding the spacecraft to vibrate in a very specific, measurable way, and the pattern of that vibration confirmed beyond doubt that Voyager 1 was surrounded by dense, cold interstellar plasma rather than the thin, hot plasma that fills the Sun's own wind. In September of 2013, NASA formally announced that Voyager 1 had left the solar system over a year earlier, becoming the first human-made object in history to do so. At the moment of that historic crossing, Voyager 1 sat about 11 billion miles from the Sun, a distance so extreme that a radio signal travelling at the speed of light still needed over 16 hours to make the one-way trip back to Earth. The spacecraft itself, powered by a slowly decaying source of nuclear energy, kept transmitting faithfully the entire time, completely unaware that it had just made history, simply continuing to do exactly what it had been built to do decades earlier. The formal announcement drew coverage from news outlets across the entire planet, marking one of the rare moments when a slow, patient science mission suddenly became front-page news everywhere at once. Reporters wanted a single dramatic photograph to run alongside the story, but no camera on Voyager 1 had captured anything visual by that point in the mission. Its cameras switched off years earlier to save power for the instruments that actually mattered out here. The real proof lived entirely in graphs and numbers, quiet data that told an enormous story without a single picture to go along with it. Stepping outside the only home your entire species has ever known is not something most people ever get to fully picture. For Voyager 1, that moment arrived after 35 years of continuous travel, following a path that took it past 2 giant planets, through a churning storm of solar wind turbulence, and finally across a boundary no spacecraft, no telescope, and no scientist had ever directly measured before. Voyager 1 made that crossing alone, the first and only ambassador humanity had ever sent beyond the edge of its own solar system. That solitude would not last forever. Its twin spacecraft, travelling an entirely different path through an entirely different direction of the bubble, was still years away from making the very same journey. Voyager 2 never followed its twin's exact path. Launched just over 2 weeks before Voyager 1, in August of 1977, it took a completely different route through the solar system, one designed to take advantage of a rare planetary alignment that happens only once every 175 years. That alignment allowed Voyager 2 to accomplish something no spacecraft before or since has managed. A single mission that flew past all 4 of the solar system's giant planets. After visiting Jupiter and Saturn alongside its twin, Voyager 2 continued onward alone, reaching Uranus in 1986 and Neptune in 1989, remaining to this day the only spacecraft ever to visit either of those 2 distant ice giants up close. That different trajectory sent Voyager 2 toward the solar system's edge along a completely different direction than Voyager 1, giving scientists a second, independent path to study. Voyager 2 crossed the termination shock in August of 2007, closer to the Sun than its twin had, at a distance of about 7.5 billion miles, confirming that the boundary sits unevenly around the solar system, rather than forming a perfect sphere. More than a decade later, on November 5th, 2018, Voyager 2 crossed the heliopause and became only the second human-made object in history to reach true interstellar space, at a distance of just over 11 billion miles from the Sun. This time, scientists did not need to wait over a year to confirm what had happened. Unlike Voyager 1, whose plasma measuring instrument had failed decades earlier, Voyager 2 still carried a fully working plasma science instrument, allowing it to directly measure the sudden jump in plasma density the moment it crossed, confirming the exit almost immediately rather than requiring an indirect solar event to settle the debate months later. Having 2 independent crossings, made from 2 different directions using 2 different sets of working instruments, gave scientists something Voyager 1 alone could never have provided. Real confirmation that the heliopause is a genuine physical boundary surrounding the entire solar system, rather than some strange coincidence detected by a single aging spacecraft. Voyager 2's data also revealed that the boundary layer is thinner in its direction than scientists had originally expected, adding new detail to the overall shape of the bubble surrounding our star. Keeping both spacecraft alive this long has required difficult choices back on Earth. Each one runs on a slowly decaying source of nuclear power that loses a small fraction of its output every single year, with no way to refuel or repair it across billions of miles of empty space. Engineers have spent recent years shutting down instruments one at a time, sacrificing certain measurements permanently in order to keep the remaining instruments running for a few more years, stretching every last watt of power as far as it can possibly go. Both spacecraft now drift through true interstellar space, decades older than their original planned mission, still transmitting, still working, having together mapped out an edge that no human being had ever directly measured before either one of them arrived there. Crossing the heliopause does not change a spacecraft's speed, its direction, or anything visible to the naked eye. It changes almost everything else, instantly, the moment the boundary is crossed. The most immediate shift shows up in particle counts. Just before crossing, instruments on both Voyager spacecraft detected solar wind particles in large numbers, the familiar background noise that had surrounded each spacecraft for the entire journey out from Earth. Within days of crossing the heliopause, that count collapsed to nearly zero. At the very same time, the count of high-energy particles arriving from elsewhere in the galaxy jumped sharply, in some measurements roughly doubling within a matter of days. It was as if a switch had been flipped, swapping one entire population of particles for a completely different one almost overnight. Temperature tells an even stranger story. Despite interstellar plasma being far less dense than the solar wind, meaning far fewer particles packed into any given space, those particles actually move with more energy on average, which translates into a higher temperature by the technical definition scientists use. It feels backward at first. A crowded room usually feels warmer than an empty one, yet out here, the nearly empty room runs hotter than the crowded one ever did, because temperature depends on how fast individual particles move, not simply how many of them are packed together in one place. Magnetic field readings shifted as well, though far more subtly than expected. Scientists had predicted a dramatic change in the direction the magnetic field pointed the moment a spacecraft left the Sun's influence and entered interstellar space. Instead, the field's direction barely changed at all, a detail that puzzled scientists for months and forced them to rely on other evidence to confirm Voyager 1's true position. That subtle shift eventually turned out to hold its own valuable clue, revealing that the Sun's magnetic field and the interstellar magnetic field beyond it happened to align more closely than anyone had predicted before either spacecraft made the crossing. Radio static picked up by sensitive instruments changed character too, shifting from the familiar hiss generated by the Sun's own turbulent wind into a steadier, quieter hum, generated instead by the thin plasma of true interstellar space, a sound so faint that scientists had to wait for a rare solar disturbance to ripple outward and make it clearly detectable at all. That near alignment surprised almost everyone involved, since nothing about the Sun and the wider galaxy suggested their magnetic fields should happen to line up so closely by pure chance. Some scientists now wonder whether the Sun's own magnetic field has quietly shaped the surrounding interstellar magnetic field over billions of years, reaching farther beyond the heliopause than anyone had previously assumed possible, blurring the line between where the Sun's true influence actually ends. Every one of these shifts adds up to the same underlying truth. The instant a spacecraft crosses the heliopause, it trades the Sun's protection for direct exposure to an environment shaped by other stars entirely, an environment carrying its own invisible danger, one that neither Voyager spacecraft had ever needed to face during more than 3 decades, spent safely tucked inside the Sun's own bubble. Step outside on a sunny afternoon and the Sun's magnetic field is quietly doing you a favour you never notice, blocking a huge share of dangerous radiation that constantly streams toward Earth from exploded stars scattered across the galaxy. That radiation is called cosmic rays, tiny particles moving at incredible speed, flung outward by some of the most violent events the universe produces, including the explosive death of massive stars far larger than our own Sun. Earth's own magnetic field provides a second layer of protection closer to home, but long before cosmic rays ever reach Earth, the Sun's much larger magnetic bubble, the heliosphere, has already deflected and weakened a significant share of them, acting like a giant umbrella stretched across the entire solar system. Once a spacecraft crosses the heliopause and leaves that umbrella behind completely, it loses that protection all at once. Both Voyager spacecraft recorded a sharp spike in cosmic ray levels the moment they crossed into true interstellar space, confirming directly what scientists had long suspected from theory alone. The Sun's bubble genuinely shields the space around it, and stepping outside that bubble means facing the galaxy's radiation at full, undiluted strength for the very first time. This matters for more than just scientific curiosity. Cosmic rays carry enough energy to damage sensitive electronics, degrade solar panels, and, given enough exposure over a long enough time, pose a genuine health risk to any living creature unlucky enough to be caught without protection. Every spacecraft humans have ever sent beyond Earth's orbit has had to account for this radiation in its design. and any future mission hoping to survive for decades in true interstellar space, the way both Voyager spacecraft have, would need shielding far heavier than anything used on a mission built to stay closer to home. Engineers are already studying a future mission built specifically to survive this environment for far longer, carrying instruments designed from the very start to operate safely inside a radiation field this intense, rather than instruments originally built for a much gentler mission closer to the Sun and only later pushed out here by accident, the way both Voyager spacecraft effectively were. Such a mission could travel faster than either Voyager, reach the true edge of the solar system sooner, and carry cameras still switched on the whole way, something neither aging spacecraft can offer any longer. Both Voyager spacecraft continue drifting through this newly hostile environment today. Decades past their original mission timeline, their aging instruments still recording higher radiation levels than anything either spacecraft ever encountered while safely tucked inside the Sun's bubble. Neither spacecraft carries a crew, and neither was ever designed with a human passenger in mind, which is fortunate, because unprotected exposure to this level of radiation for any extended stretch of time would pose a serious danger to a living person. Both spacecraft still have one enormous stretch of territory left to cross before reaching anything resembling another star system, an emptiness so vast and so quiet that even the term interstellar space undersells just how little actually fills it, guarded at its outer edge by an ancient frozen shell of comets that no spacecraft built by humans has ever come anywhere close to reaching. Guarding the outer edge of the solar system is a structure so large that everything explored so far, every planet, every moon, and even the entire heliosphere itself, fits inside it like a single pebble resting inside a stadium. Scientists call it the Oort cloud, a vast shell made of trillions of icy comets surrounding the Sun in every direction at once. Nobody has ever photographed this cloud directly. It sits far too distant and far too dark for any telescope built so far to resolve individual objects within it. Its existence was worked out mathematically in 1950 by an astronomer studying the orbits of long-period comets that swing through the inner solar system only once every few thousand years. He noticed that these comets kept arriving from every direction in the sky, evenly scattered rather than clustered along one path, and realised the only way to explain that pattern was a giant spherical shell of icy bodies surrounding the entire solar system, quietly supplying new comets one at a time whenever gravity gave one of them a nudge. Every object inside this cloud formed close to the Sun billions of years ago, alongside every planet and every world already explored on this journey. Gravitational encounters with the giant planets, especially Jupiter and Saturn, flung countless icy bodies outward during the solar system's early, chaotic youth, scattering them across distances so extreme that many ended up locked into orbits reaching trillions of miles from the Sun. What remains today is a shell built entirely from leftovers, the true edge of the Sun's gravitational reach. The scale involved is difficult to compare to anything explored earlier in this journey. Every icy world discussed so far, Pluto, Eris, Sedna, even the entire Kuiper belt sits closer to the Sun than the inner boundary of this cloud even begins. The heliosphere itself, the enormous bubble of solar wind that took 2 spacecraft over 3 decades to cross, would need to be scaled up several hundred times over just to reach partway into this shell of comets. Despite containing an estimated trillion or more individual objects, the Oort cloud remains almost entirely empty space by volume. Individual comets sit millions of miles apart from their nearest neighbours, drifting so slowly and so quietly that a spacecraft could pass directly through the heart of this cloud and have essentially no chance of ever coming close enough to see one. This shell does not simply guard the solar system, it quietly supplies it, feeding a slow, steady trickle of comets inward whenever the gravity of a passing star or the gentle pull of the galaxy itself nudges one loose from its billion-year orbit and sends it tumbling toward the Sun for the first time since the solar system was born. Reaching even the closest edge of this enormous shell would demand a kind of patience no human spacecraft has ever needed to summon before. A journey measured not in years or even centuries, but in a span of time that stretches past nearly every recorded chapter of human history combined. Voyager 1 is currently travelling faster than almost anything else humanity has ever built, covering roughly 3.5 times the distance from the Sun to Earth every single year. Even at that blistering pace, reaching the inner edge of the Oort cloud would take about 300 years, a wait longer than the entire history of powered flight, stretched out again nearly 3 times over. 300 years sounds enormous already, yet it barely qualifies as a beginning. The inner edge of the Oort cloud marks only the first icy bodies belonging to this shell, not its true depth. Fully crossing through the cloud, from its closest icy neighbours to its farthest outer stragglers, would take a spacecraft travelling at Voyager's speed roughly 30,000 years, a stretch of time longer than the entire span of recorded human civilization, longer than agriculture, longer than the written word, longer than every city ever built from the ground up. To put that number into a shape a human mind can actually hold, imagine every generation of your own family going back to the very first humans who ever painted an animal on a cave wall. Multiply the number of centuries separating you from those early painters by roughly 10, and that is roughly how long a single spacecraft, moving at Voyager's exact speed, would need just to pass fully through this shell of comets before finally reaching open interstellar space on the other side. No spacecraft ever built by humans, including either Voyager, is actually aimed at the Oort cloud's inner edge with any scientific purpose in mind. Both spacecraft happen to be heading in a general direction that will eventually carry them through the outer fringes of this region, purely as a side effect of the trajectory chosen decades ago to fly past Jupiter and Saturn, not because any mission planner specifically aimed for it. This timescale forces an uncomfortable realization about the entire idea of leaving the solar system. Crossing the heliopause, the milestone both Voyager spacecraft already achieved, sounds dramatic, and it genuinely is. Yet by the strict definition many astronomers actually use, based on where the Sun's gravity, not simply its wind, finally loses its grip, neither spacecraft has come anywhere close to leaving the solar system at all. Both are still deep inside the Sun's true territory, decades into a journey that has not even reached 1% of the total distance required. A useful way to hold that number in your head. Imagine every single day since the invention of the wheel, then multiply that entire stretch of history by roughly 10. That rough multiple is close to how many days would pass before a Voyager-style spacecraft finished crossing the Oort cloud from end to end, a wait so long that entire languages could rise, spread across a planet and vanish again before the journey reached its halfway point. Understanding exactly where that true gravitational boundary sits, the actual point where the Sun finally lets go, requires stepping back from spacecraft entirely and thinking instead about gravity itself, a force that never fully disappears, only fades slowly, quietly, across a distance too enormous for any single number to capture cleanly. Gravity never switches off completely. Move far enough from any object and its pull grows weaker and weaker, yet by the actual laws of physics, it never reaches a hard stop at exactly zero, no matter how far away you travel. That creates a real challenge for anyone trying to draw a firm, final line around the true edge of the solar system. Astronomers solve this problem by comparing forces rather than searching for a point where gravity vanishes entirely. At some distance from the Sun, its gravitational pull on a passing object becomes weaker than the combined pull of every other star in the galaxy, tugging in different directions. Past that point, an object drifting freely would more likely drift towards some other star's gravity, or simply toward the galaxy's overall pull, rather than remaining loosely bound to the Sun. That distance marks the true, final edge of the Sun's territory, often placed somewhere between 1 and 2 light-years from the Sun, roughly halfway to the nearest neighbouring star system. That distance dwarfs everything covered in this journey so far. The heliopause, reached by both Voyager spacecraft after 35 years of travel, sits about 11 billion miles from the Sun. The Sun's true gravitational edge sits roughly 6 trillion miles out, over 500 times farther than the heliopause itself. Every mile explored across every chapter of this journey combined, from Pluto through the scattered disk and across the entire heliosphere, would still fit inside just a small fraction of the remaining distance left to travel. At this outer boundary, an object no longer feels itself clearly belonging to any single star. It drifts in a kind of gravitational no man's land, tugged weakly and almost equally by countless stars scattered across the surrounding stretch of the galaxy, none of them pulling hard enough to claim it firmly as their own. Some of the icy bodies scattered throughout the outer Oort cloud sit close enough to this boundary that a sufficiently strong nudge from a passing star or a shift in the galaxy's tide could knock them free of the Sun entirely, sending them drifting alone through interstellar space forever, belonging to no star at all. Astronomers arrived at this boundary using a method borrowed from a much older branch of physics, one originally developed to describe how moons stay locked around planets, rather than drifting free into space around the Sun instead. Applying the exact same math to the Sun itself, scaled up to compare its pull against the combined pull of every neighbouring star, produces the enormous distance now treated as the honest, physically grounded edge of the entire solar system. This is the true, final answer to the question that opened this entire journey. The edge of the solar system is not a wall a spacecraft crashes into, nor a single dramatic crossing captured in a single day of data. It is a slow fade, stretched across trillions of miles, ending in a boundary so faint that gravity itself struggles to draw a clean line through it. Somewhere out in that faint, faraway boundary, a comet drifts quietly along an orbit it has held for billions of years, until something finally disturbs it enough to send it falling inward for the very first time since the solar system was born. The trigger is rarely dramatic. Sometimes a star passes close enough to the outer solar system, even from several light years away, for its gravity to gently tug a comet loose from its distant orbit. Other times the disturbance comes from the galaxy itself, a slow, steady tidal pull generated by the combined mass of billions of stars stretched across the Milky Way, strong enough over millions of years to nudge the most loosely held comets free without any single dramatic event required at all. Once nudged loose, a comet begins an almost unimaginably long fall toward the Sun, a journey that can take hundreds of thousands, sometimes millions of years to complete, drifting silently through the coldest, emptiest reaches of the solar system the entire time. For nearly the entire fall, nothing visible happens at all. The comet remains a frozen, dark chunk of ice and dust, indistinguishable from the empty space surrounding it, giving off no light, no tail, and no warning of its approach. Everything changes only in the final stretch of that journey, once the comet finally passes close enough to the Sun for real warmth to reach it for the first time in its entire existence. Frozen gases trapped inside the comet's core begin turning directly into vapour, streaming outward and carrying dust along with them, building the glowing head and the long flowing tail that make a comet visible from Earth. That glow, brief and spectacular, represents only the very last flicker of a journey that began long before any currently living human or their most distant ancestors ever existed. Some of the most famous comets in recorded history followed exactly this path, arriving suddenly and unexpectedly from the depths of the outer solar system, blazing brightly for a few months, then vanishing again on an orbit so long that nobody currently alive will ever witness their return. Once a long-period comet finally swings back out past the planets, it begins the exact same slow fall in reverse, heading back toward the shell of ice it originally came from, not to be seen again for tens of thousands of years, if it ever returns at all. A handful of these long-distance travellers never make it back out at all. Occasionally the same gravity that first sent a comet falling inward also bends its path just enough to send it slamming directly into a planet, or close enough to the Sun to break apart entirely, scattering fragments across an orbit that once belonged to a single, ancient object. Evidence of exactly this kind of collision has been found scattered across the surfaces of several planets and moons throughout the solar system, silent reminders that some of these long journeys end in impact rather than a graceful return trip back to the outer dark. Every one of these comets carries a message of its own, a frozen sample of the exact material the solar system was built from, preserved almost perfectly since before Earth had an atmosphere, a moon, or a single living cell. Studying one, even briefly, offers a clearer window into the solar system's earliest days than nearly anything else scientists have ever managed to examine directly. Everything explored across this entire journey, every planet, every icy world, the whole breathing bubble of the heliosphere, and the vast shell of comets surrounding it, still belongs to a single star system. Step back far enough, and that entire system shrinks down to a single point of light, one among hundreds of billions scattered across the galaxy. The nearest star to the Sun is called Proxima Centauri, and even that word nearest deserves a serious reality check. Proxima Centauri sits about 4.25 light-years away, a distance so extreme that expressing it in miles produces a number nobody can meaningfully picture. Roughly 25 trillion miles. Light itself, the fastest thing that exists anywhere in the universe, needs over 4 years just to make that one-way trip. Scale the entire distance from the Sun to the outer edge of its own gravitational territory, the true boundary explored earlier in this journey, down to the length of a single football field. On that same scale, Proxima Centauri would sit only about 2 football fields farther away, practically a neighbour by comparison to the true emptiness that fills most of the galaxy. Yet reaching that neighbour with anything humans have ever built would still take longer than the entire span of recorded human history several times over. Proxima Centauri is not travelling alone either. It belongs to a group of 3 stars orbiting one another, together known as the Alpha Centauri system, discovered as a distinct star system centuries ago, though Proxima itself, being far dimmer than its 2 brighter companions, was not identified as a separate star until the early 20th century. In the years since, astronomers have confirmed at least one planet orbiting Proxima Centauri directly, sitting in a zone where liquid water could theoretically exist on its surface, a discovery that instantly made this closest of all neighbouring stars one of the most closely studied targets in the entire search for worlds beyond the solar system. Despite being the closest star to the Sun, Proxima Centauri remains almost entirely out of reach using any spacecraft currently in existence. The emptiness separating one star system from another is not simply large. It is large enough that the very idea of distance starts to lose its everyday meaning, stretching into a scale better suited to comparing entire star systems than comparing points on a map. Proxima Centauri's 2 brighter companion stars, together forming the rest of the Alpha Centauri system, are themselves a familiar sight to anyone standing under a clear night sky in the southern hemisphere, appearing to the naked eye as a single, unusually bright star. Only when viewed through a telescope does that single point of light separate into its true components, a reminder that even the nearest stars in the entire sky still sit far too close together from Earth's point of view for the unaided human eye to ever tell them apart. Somewhere between the frozen comets of the outer Oort cloud and the star Proxima Centauri itself lies a stretch of true interstellar emptiness, colder and quieter than anything encountered so far on this journey, a gap so enormous that closing it would test the absolute limits of everything humans have ever managed to build and launch into space. Closing the gap between the solar system and its nearest neighbouring star is not simply a matter of building a faster rocket. It is a problem that pushes directly against the hardest physical limits currently known to science. Voyager 1, still the fastest object ever aimed in the general direction of another star system, travels at roughly 38,000 miles per hour, At that speed, reaching Proxima Centauri would take a staggering 73,000 years, a span of time longer than the entire history of modern humans living in organised societies, stretched out several times over. Voyager 1 is not actually headed toward Proxima Centauri at all. Its current trajectory will instead carry it in about 40,000 years, within roughly 1.5 light years of a dim, unremarkable star, a distance still far too great for any meaningful encounter, simply the closest pass its current path happens to produce. Even using the fastest realistic technology scientists currently consider plausible, rather than anything already built and flying, the numbers barely improve. A spacecraft capable of reaching 1/10 the speed of light, a velocity far beyond anything ever achieved by a human-made object, would still need over 40 years just to complete the one-way trip to Proxima Centauri. Reaching even that extreme speed would require an amount of energy and propulsion technology that remains entirely theoretical today, existing only in engineering proposals and physics papers rather than any spacecraft currently under construction. Slow the pace down to something resembling achievable engineering, and the wait stretches into a length of time that no single human lifetime, or even several lifetimes chained together, could realistically span. A journey lasting tens of thousands of years would require a spacecraft, or a series of spacecraft, capable of operating reliably across a length of time longer than every recorded civilization in human history combined, with no possibility of repair, resupply, or rescue at any point along the way. This is not a limitation unique to human engineering, or a problem likely to be solved simply by inventing a slightly better rocket engine somewhere down the line. It is a direct consequence of just how enormous the true emptiness between stars actually is, a gap that dwarfs every distance explored earlier across this entire journey combined. Even generational travel, the idea of launching a crew who would never themselves arrive, instead raising children and grandchildren aboard the same spacecraft until some distant descendant finally reached the destination, generations later, runs into the exact same wall. No propulsion system currently available could push a spacecraft large enough to support a living, breathing community across that kind of distance fast enough to make the idea practical, and no material yet built could keep something that large and that complex running safely for tens of thousands of uninterrupted years. Faced with numbers this extreme, engineers decided decades ago that a spacecraft alone could never carry the full weight of this journey. If distance itself made physical travel nearly impossible within any human timescale, then perhaps a different kind of traveller, one built from nothing more than sound, image, and careful intention, stood a better chance of actually making it all the way across. Bolted to the side of Voyager 1 and Voyager 2 rides a disk unlike anything else ever launched into space, a physical object built with the specific intention of surviving and remaining understandable across a length of time longer than human civilization itself has existed. The disk is made of gold-plated copper, chosen specifically because that combination resists corrosion and decay far longer than nearly any other material available at the time. Engraved directly onto its surface are simple diagrams explaining exactly how to build a working record player and play the disc back correctly, along with a symbolic map showing Earth's location relative to a set of distinct, easily identifiable stars, designed to remain accurate and readable across tens of thousands of years, even as the positions of nearby stars slowly shift. A team of scientists and artists, led by an astronomer well known for popularizing space science to the public, spent only a matter of weeks assembling the disk's actual contents before the strict launch deadline arrived. Choosing what to include sparked genuine, sometimes heated disagreement among the team. Every recording included had to represent something meaningful about life on Earth, using a format that any future finder, almost certainly not human, and quite possibly not even biological in any familiar sense, might have some realistic chance of eventually decoding. The final disc carries greetings recorded in dozens of different human languages, a carefully chosen selection of music representing cultures scattered across the entire planet. natural sounds recorded directly from Earth itself, including wind, thunder, and the calls of animals, and a series of encoded photographs depicting daily human life, covering everything from simple diagrams of basic mathematics through images of cities, farms, and family life. Every person directly involved in building this disk understood, clearly and without illusion, that the odds of it ever actually being found by anyone at all were vanishingly small. Interstellar space is staggeringly empty, and neither Voyager spacecraft is aimed with any real precision toward another star system. Despite that, the team built the record anyway, choosing to treat the attempt itself, the simple act of trying to speak clearly across an ocean of empty space and empty time, as worth making regardless of whether anyone would ever actually hear it. Every photograph included on the disc had to be converted first into a format resembling a very simple, early television signal, encoded directly as sound so that any future finder capable of building basic playback equipment could theoretically decode the images by converting that sound back into a picture line by line, without ever needing any written instructions written in human language at all. The record was never designed to be replayed by human hands or heard by human ears ever again. It was built for a future so distant that Earth itself may look completely different by the time, if ever, anyone manages to find and understand it, a message launched not toward any single destination, but simply outward, into the dark, on the slim chance that outward eventually leads somewhere. Despite carrying a message built to last for eons, both Voyager spacecraft remain firmly rooted in the present, still quietly gathering fresh data today, well over 4.5 decades after they first left Earth. As of right now, Voyager 1 has only 2 working science instruments remaining active out of the 10 it originally carried. One measures the surrounding magnetic field directly. The other listens for faint vibrations travelling through the thin plasma that fills interstellar space, a kind of vibration triggered occasionally by powerful bursts of activity erupting from the sun itself, rippling outward for more than a year before finally reaching the spacecraft and setting the surrounding plasma gently humming. Every other instrument once carried on board has already been shut down permanently, sacrificed one at a time to squeeze a little more operating life out of a power supply that keeps shrinking every single year. Voyager 2 carries slightly more working instruments still, thanks to a marginally healthier power supply and a shorter overall distance from Earth, though engineers have been forced to make the exact same difficult trade-offs, shutting down one instrument after another according to a careful plan drawn up years in advance by the mission team, ranking every instrument by scientific value long before any actual shutdown became necessary. Both spacecraft rely entirely on the slow, steady decay of a small amount of radioactive material sealed safely inside each one, converting heat released by that decay directly into electricity. That process never fully stops, yet it produces less and less usable power with every passing year, a permanent, irreversible decline built into the very physics of how the spacecraft generate electricity in the first place. Engineers have recently tested a bold new approach, nicknamed after the very beginning of the universe itself, attempting to squeeze extra operating margin out of backup circuits originally installed purely as a safety measure decades ago, hoping the trick might even allow a previously shut down instrument to switch back on. Every single command sent to either spacecraft today takes close to a full day just to arrive, and any response takes an equally long stretch of time to travel back, meaning every decision made by the mission team has to account for a conversation that unfolds far slower than anything resembling a normal, real-time exchange between two people. Engineers have grown remarkably resourceful at stretching every remaining watt as far as it can possibly go, repurposing backup power circuits originally installed purely as a safety precaution. Decades ago, circuits nobody ever expected the mission would still need to lean on this far into its lifetime. Every successful trick buys additional months, sometimes additional years, though each one also carries real risk, since a spacecraft billions of miles away cannot simply be repaired if a command sent across that distance does not behave exactly as planned. Despite every setback, every power cut, and every year that passes, both spacecraft continue reporting back faithfully from a region of space no other operating mission has ever managed to reach directly, a signal from the true edge of human exploration that grows fainter and more precious with every year that passes. Every signal Voyager 1 and Voyager 2 currently send back to Earth will not last forever. Somewhere in the decade ahead, engineers expect the last remaining instrument on each spacecraft to finally lose power completely, closing out one of the longest-running science missions in human history. The math behind that ending is simple and unforgiving. Each spacecraft loses a small, steady amount of electrical power every single year, a direct result of the radioactive material powering it slowly decaying, a process that cannot be paused, reversed, or refueled from a distance of billions of miles. Engineers have already shut down every instrument they consider non-essential, keeping only the bare minimum still running, and even that minimum continues shrinking year after year with no way to stop it. When that final instrument eventually loses power for good, the spacecraft itself will not necessarily fall completely silent right away. A basic radio transmitter, requiring far less power than any of the actual science instruments, may continue sending a faint, simple signal back toward Earth for some additional stretch of time afterward, carrying no new scientific data at all, simply confirming that the spacecraft still exists and still functions on the most basic level possible. Eventually, even that signal will fade below the point where any receiver on Earth, no matter how sensitive, can still detect it. At that moment, both Voyager spacecraft will not stop existing. They will not explode, crumble, or vanish in any dramatic fashion. They will simply continue drifting silently through interstellar space exactly as they have for decades, still carrying their golden records, still carrying their engraved star maps, no longer able to report anything back to the species that built them, yet still physically present, still moving outward at the exact same steady speed they have held since leaving the solar system behind. Mission engineers already know, with complete certainty, that this ending is coming. What remains genuinely uncertain is the exact date, since unexpected technical problems could shorten the timeline suddenly, while a successful power-saving trick could stretch it out a little longer than currently expected. Either way, the window remaining for either spacecraft to keep speaking to Earth is now measured in years, not decades, a countdown that began the moment each spacecraft first launched, and one that has been quietly ticking down ever since. Mission engineers describe the entire final stretch of this mission, using a word usually reserved for living things nearing the end of a long, full life: graceful. Every remaining decision focuses less on stopping the inevitable and more on making sure each spacecraft spends its last working years doing the most valuable science still possible, right up until the very last watt of power finally runs dry. When that final transmission eventually goes silent, humanity will lose its only direct, real-time source of information from beyond the edge of its own solar system, at least until another spacecraft, built specifically to survive even longer and travel even faster, someday follows the exact same path outward. While two aging spacecraft prepare for their own eventual silence, something else has been quietly arriving from the opposite direction, drifting into the solar system from interstellar space entirely uninvited. In the fall of 2017, astronomers spotted a strange, fast-moving object streaking through the inner solar system on a path no ordinary asteroid or comet could ever follow, a trajectory too steep, too fast, and too clearly not bound by the sun's gravity at all. Named using a word meaning scout or messenger, this object became the very first confirmed visitor from another star system ever detected passing through our own, tumbling end over end, unusually elongated in shape, and, most puzzling of all, accelerating slightly as it left the inner solar system in a way ordinary gravity alone could not fully explain. A second confirmed interstellar visitor arrived just 2 years later, in 2019, this time clearly identified as an active comet from the moment it was discovered, complete with a glowing tail and a visible cloud of gas and dust streaming off its surface, offering scientists a far clearer look at genuine material that had formed around another star entirely. A third confirmed visitor arrived even more recently, first spotted in the summer of 2025 by a telescope network built specifically to hunt for exactly this kind of object. This latest visitor turned out to be unusually large compared to the first two, with a core stretching possibly several miles across, and scientists studying its trajectory concluded it may be extraordinarily old, potentially billions of years older than the Sun itself, having formed in a distant, ancient region of the galaxy long before our own solar system ever came together. It passed safely within a few million miles of Mars in the fall of that same year, then made its closest approach to Earth in December, before continuing on an outbound path that will carry it back into interstellar space forever, never to return. The very first of these three visitors sparked genuine, serious scientific debate over its unusual shape and unexplained acceleration, with a small number of researchers openly wondering whether it could represent artificial technology rather than a natural object. The overwhelming majority of scientists who studied the available data concluded it was almost certainly a natural body, likely a fragment of ice and rock shaped by billions of years of travel, though the lingering uncertainty surrounding that very first visitor helped fuel intense public interest in every interstellar object discovered since. Each of these three visitors confirmed something remarkable. Material from other star systems genuinely does drift through our own from time to time, carried along by the same slow, random currents of gravity and motion that scatter material throughout the entire galaxy. Every one of them arrived completely unannounced, detected only by chance, using telescopes that happened to be scanning the right patch of sky at exactly the right moment. If objects like these can drift quietly into our solar system without any warning at all, then somewhere out among the countless stars scattered across the galaxy, pieces of our own solar system, or even the message riding aboard Voyager itself, may already be drifting past worlds no human has ever seen, completely unnoticed, the same way these three visitors slipped past us. If material can drift silently into the solar system from other stars, then sending something the other direction, deliberately and on purpose, is no longer simply theoretical. Several serious proposals already exist for exactly that kind of mission, each one designed to travel farther, faster, and smarter than either Voyager spacecraft ever could. One of the most ambitious proposals involves building an enormous array of powerful lasers on the ground, all aimed at a single tiny spacecraft weighing barely more than a smartphone, attached to an extremely thin, lightweight sail only a few atoms thick. Firing every laser at once for just a few minutes could theoretically push that tiny spacecraft up to roughly 1/5 the speed of light, a velocity that would let it reach the Alpha Centauri star system, home to Proxima Centauri, in roughly 20 years rather than tens of thousands. The concept remains firmly in the research and testing phase today, with no full-scale mission yet built or launched, though smaller-scale demonstrations of the underlying laser and sail technology continue moving forward. A separate, more immediate proposal involves building a single dedicated spacecraft, specifically designed to study the heliosphere from the outside, launching with far more advanced propulsion than either Voyager carried, and reaching the heliopause in a fraction of the time it took either aging spacecraft to get there. Rather than stumbling into interstellar space as an unplanned side effect of a planetary flyby mission, as both Voyager spacecraft essentially did, this kind of purpose-built mission would carry instruments specifically chosen to study the boundary itself in far greater detail than anything Voyager's aging 1970s technology could ever manage. Every one of these proposals shares a common motivation. Both Voyager spacecraft succeeded far beyond anything their original designers ever expected, yet they were never actually built for this exact job, and their 1970s-era instruments are approaching the absolute limit of what decades-old technology can accomplish this far from home. A mission built specifically for interstellar exploration from the very beginning could gather sharper, more complete data using instruments purpose made for exactly this environment, rather than instruments originally intended for flybys of Jupiter and Saturn, pressed into service decades beyond their original assignment. A working laser sail small enough to fit in the palm of a hand still needs to survive an environment every bit as harsh as the one already explored across this entire journey, including direct exposure to the same intense cosmic radiation that stripped away the Sun's protection the moment both Voyager spacecraft crossed the heliopause decades ago. Engineers working on these proposals study the exact same data both Voyager spacecraft have already gathered, using real measurements from the true edge of the solar system to design instruments and shielding for a mission that has not yet left the drawing board. None of these future missions currently have a firm launch date, and every one of them still faces enormous technical and financial hurdles before ever leaving the ground. Yet simply having serious proposals on the table marks a real shift in ambition, evidence that engineers are no longer content to let two aging accidental pioneers remain humanity's only real witnesses to the space beyond the solar system's edge. Even the most ambitious mission ever proposed, capable of crossing to another star system in mere decades instead of millennia, would still barely register as a rounding error on the true scale of the galaxy surrounding it. The Milky Way stretches across roughly 100,000 light-years from one edge to the other, a number so large that even converting it into miles produces a figure with far too many digits to hold any real meaning in a single glance. Packed inside that enormous disk sits somewhere between 100 billion and 400 billion individual stars, each one a sun in its own right, many almost certainly surrounded by their own family of orbiting planets, their own version of a heliosphere, and quite possibly their own version of an Oort cloud guarding their own outer edge. The Sun itself is not sitting near the centre of this galaxy, nor anywhere close to its outer fringe. It occupies a fairly ordinary location roughly halfway out, tucked inside one of several spiral arms winding around the galaxy's much denser core. Even at that seemingly average position, the Sun still sits an enormous distance from the crowded galactic centre, a region packed far more densely with stars, and one considered far too dangerous and chaotic for a planet like Earth to have ever safely formed and stayed stable long enough for life to develop. The entire Sun, along with every planet, moon and icy world explored across this entire journey, is not sitting still within this galaxy either. It orbits the distant galactic centre continuously, tracing an enormous slow circle that takes roughly 230 million years to complete just once, meaning the Sun and everything orbiting it has only completed a small handful of full laps around the galaxy since the very first simple life appeared on Earth billions of years ago. Set against a structure this immense, the entire journey explored across every chapter so far, from Pluto through the heliopause, past the Oort cloud, and out toward the nearest star, still occupies only the tiniest, most immediate corner of a single spiral arm belonging to just one ordinary galaxy among hundreds of billions of other galaxies scattered across the wider universe. Reaching even the closest neighbouring star system would carry a spacecraft only the shortest possible hop across a galaxy that would still take that same spacecraft billions of years to fully cross from end to end. Standing on a clear, dark night and looking up at the pale band of light stretching across the sky, that feature ancient civilizations across the world named after milk or rivers or paths of the dead, you're actually looking edge-on into the very disk. This entire journey has been trying to place in context a slice through hundreds of billions of other suns, viewed from a small, unremarkable position roughly halfway out toward the rim. Faced with distances this extreme, a different question naturally follows. If humans ever did manage to send a message far enough to actually reach another star system, what exactly would a reply, assuming one ever came at all, actually look like by the time it eventually made its way back home? Sending a message toward another star is only half the challenge. Receiving any kind of reply, if one ever came at all, would demand a level of patience that stretches far beyond any single human lifetime. Radio waves, like every other form of light, travel at the same fixed, unbeatable speed, no matter how powerful the transmitter sending them happens to be. A message aimed directly at Proxima Centauri today would take just over 4 years to arrive, assuming anything out there happened to be listening in exactly the right direction at exactly the right moment. Any reply sent back immediately would then need another 4 years to make its own way home, meaning the fastest possible complete exchange, a single question followed by a single answer, would take at minimum 8.5 years from start to finish, and only if every other star turned out to be far closer than most of the galaxy actually is. For decades, scientists have pointed enormous radio telescopes toward the sky, listening carefully for any signal that might indicate an intelligent origin, rather than the ordinary background noise produced naturally by stars, gas clouds, and other predictable astronomical sources. So far, no confirmed signal of that kind has ever been detected, despite scanning a meaningful portion of the sky using instruments sensitive enough to catch even extremely faint transmissions from relatively nearby stars. The silence itself does not prove very much either way. The galaxy is so enormous, and the portion of it carefully searched so far so comparatively small, that the absence of a detected signal remains just as consistent with genuine emptiness as it does with a galaxy quietly full of civilizations simply too far away, too different, or too disinterested to have ever sent anything detectable in our specific direction, using a method humans currently know how to detect. If a genuine reply to any human signal, including the golden record currently riding aboard both Voyager spacecraft, ever did arrive, the wait involved would almost certainly stretch across many human lifetimes rather than a single one. Whoever eventually received that reply back on Earth, if Earth even still exists in any recognizable form by then, would be receiving a message crafted by beings responding to a version of humanity that might no longer closely resemble whoever happens to be listening at the time. That enormous gap between sending and receiving does not make the attempt pointless. It simply reframes exactly what kind of message a golden record, or any future signal aimed outward, is actually built to be. Not a conversation expecting a quick reply, but a long, patient message launched outward on the small chance that distance and time eventually stop mattering, even if neither its senders nor its earliest listeners are ever still around to witness the moment it finally does. Some scientists have proposed a different approach entirely, one that skips radio waves altogether and simply lets physical objects carry the message instead, the exact same strategy already riding aboard both Voyager spacecraft. A slowly drifting golden record requires no ongoing transmitter, no continued funding, and no working civilization back home to keep sending updates. It simply waits, patiently, for however long it takes, carrying its message intact regardless of what happens to the species that built it in the meantime. Long after every human currently alive has passed away, long after the last working instrument aboard either Voyager spacecraft finally loses power for good, both spacecraft will still be out there, drifting silently through the vast emptiness separating one star system from another. Neither spacecraft faces any real risk of colliding with anything along its outward path. Interstellar space is staggeringly, almost incomprehensibly empty, meaning both Voyager spacecraft could realistically continue drifting, completely undisturbed, for billions of years without ever striking so much as a speck of dust large enough to cause any real damage. Barring an extraordinarily unlikely direct hit from a stray object, both spacecraft should remain physically intact for a length of time that dwarfs the entire history of life on Earth. The golden record riding aboard each spacecraft was specifically engineered with that kind of timescale in mind. Its gold-plated copper surface resists corrosion far longer than nearly any material readily available at the time it was built, and the protective aluminum jacket surrounding it was designed to shield the recording itself from damage caused by cosmic radiation and stray dust impacts for well over 1 billion years. long after Earth's surface has been reshaped by continental drift beyond recognition, long after every language currently spoken has changed beyond recognition or vanished completely. That record will very likely still exist, sealed and largely intact, drifting quietly through the galaxy. The Sun itself is expected to remain a stable, steadily burning star for several billion more years, before eventually swelling into a much larger, cooler star, a transformation expected to consume Mercury, Venus, and possibly Earth itself in the distant future. By the time that transformation eventually happens, both Voyager spacecraft will already sit safely, unimaginably far beyond any danger the dying Sun could ever pose, having left that entire fate behind billions of years earlier, still drifting outward at exactly the same steady speed they have held since first leaving Earth behind. Neither spacecraft will ever pass close enough to another star system to be pulled into orbit around a different sun based on their current trajectories. Both are destined to drift forever through the open space between stars, never captured, never landing, never stopping, carried along indefinitely by nothing more than the same momentum they picked up decades ago during a handful of close flybys past Jupiter and Saturn. In a very real sense, both spacecraft are now more durable and potentially far longer lived than the civilization that built them, than the planet that launched them, and quite possibly than the Sun itself. Two machines built using technology from the 1970s, running on computers weaker than anything found in a modern kitchen appliance, may end up outlasting almost everything else connected to their own origin story, silently carrying humanity's chosen message outward long after every trace of the species that sent it has changed beyond recognition or vanished from Earth entirely. Everything explored across this entire journey, every planet, every icy world, every violent boundary crossed, and every fact carried home by two aging spacecraft, adds up to something larger than a simple list of destinations. It adds up to the very first real step humanity has ever taken outside its own home. For nearly the entire span of human history, the solar system itself represented the absolute limit of what anyone could meaningfully explore, first by eye, then by telescope, and eventually by spacecraft capable of actually visiting other worlds directly. Crossing the heliopause changed that limit permanently. For the first time ever, a piece of human-made technology, carrying a message deliberately built to represent the entire species, physically left the neighborhood the Sun controls and entered a region shaped instead by the wider galaxy. That achievement did not require warp drives, faster-than-light travel, or any of the dramatic shortcuts often imagined in stories about leaving a home star system behind. It required patience, careful engineering, and a willingness to keep a decades-old spacecraft alive far longer than anyone originally expected, squeezing every last useful year out of technology built, using tools far simpler than what sits inside a modern phone. The true significance of this journey may not become fully clear for a very long time. Both Voyager spacecraft will eventually fall silent, their instruments exhausted, their transmitters finally too weak to reach Earth. Yet the golden records they carry, along with the physical spacecraft themselves, will continue drifting long after that silence begins, representing a species that reached beyond its own star, deliberately, on purpose, even knowing full well that nobody currently alive would ever witness whatever, if anything, eventually happened next. This shift in ambition matters beyond the specific hardware involved. A species capable of planning missions expected to operate for tens of thousands of years, or capable of building a physical message intended to outlast its own home planet, is a species thinking about its own existence on a genuinely different timescale than the one most daily decisions get made on. Leaving the solar system, even just symbolically, forces a kind of long view that rarely gets applied to anything else. Every future mission discussed across this journey, from laser-propelled sails capable of reaching another star system within a single human lifetime, to purpose-built probes designed specifically to study the true edge of the solar system, represents a continuation of exactly this same impulse. the decision to keep reaching outward, regardless of how long the journey takes or how unlikely any eventual discovery might be. You began this journey standing still, apparently, while actually moving faster than a bullet, carried along by a planet orbiting a star that itself orbits a galaxy stretching far beyond anything easily imagined. You have now followed that same outward path across every world, every boundary, and every spacecraft that has ever attempted it, all the way to the true edge of everything the sun can claim as its own. The wall has already been crossed. The message is already out there, drifting, patient and silent, carrying humanity's voice outward into a darkness large enough to hold it for as long as it takes for that darkness to finally answer back.